Maybe it's like this. Maybe it's like that. So have you guys heard about that research about talent is overrated? I think I mentioned that earlier this semester. Talent is overrated, and then...
It's all about people you know.
Well, no, that's something else. No, that's that last part, but talent is overrated. And it says that it's really practice which helps you achieve what you want to achieve. Okay, so, and then there's I think he's a psychologist in Florida. He's done quite a bit of research. He says the thing is it's 10,000 hours. So 10,000 hours then you get from practice makes you become an expert at what you do. So, although there's not 10,000 hours in a semester, I'm hoping if you put in, say, let's see, 2 hours outside of class or every hour inside of class, I hope that'll get you where you want to go. Okay, so it's really the amount of work that you put in. And as long as you believe that the amount of work that you put into something pays off in the end, I think that's all you need to believe. If you think that you're going to get by on talent only, at some point you're going to hit a wall and plateau, and that's going to be it. Okay, so even if you look at athletes, even the best athletes, they may be able to jump high and run fast, but if they can't develop their skills, then they're not going to do as well as someone who works very hard. Okay, so hard work is something you want to do, which hopefully will show off at the end and pay the dividends that you want to pay. Okay. Are there any other comments or questions on the exam? Okay, so last week before the exam we were talking about chemical equilibrium, and we know that we can make an equilibrium reaction shift in one direction or the other direction by applying a stress to a reaction. So a stress can either be adding a reactant or product, or removing a reactant or product, or increasing the temperature or decreasing the temperature, or if gases are involved, we can change the pressure. So let's take a look at how we can apply Le Chatelier's principle to how Drano works. Does anyone ever use Drano to unclog their drain?
Yeah.
Before? Does it work?
Yeah.
Does it work? Note that there was a scene in Dirty Harry in the, Clint Eastwood was the local celebrity in Dirty Harry where there was Drano was used. Remember that scene? I think it was cut. That scene was deleted if you saw Dirty Harry on TV because the scene involved pouring Drano down someone's mouth. It didn't unclog the person's. There was another function to that Drano in that scene. But anyway, the way Drano works is that Drano consists of aluminum filings and sodium hydroxide pellets. So this is actually solid Drano. There's liquid Drano now. When water is added to the Drano, the heat produced melts and saponifies the fat that clogs the drain. So if you imagine a drain looking like this. Okay, so here's your drain. Okay, so here's your sink and here's the drain. So here's the little. Okay, so here's the fat or hair that clogs the drain. Okay, so what you want to do, you pour Drano down there. So you have your Drano. And it says here again that the heat produced melts and saponifies the fat that clogs the drain. So here's a chemical reaction. Would you expect this reaction to have a large equilibrium constant or a small one? Why small? Actually, let me see a show of hands. How many of you used Drano before? Okay, so those of you who use Drano, I think can probably better answer this question because then you've seen what happens when you use the Drano. Now, when you use Drano, was it the solid Drano or the liquid Drano?
Liquid.
Oh, see, that's the thing here. So, well, when you use the liquid Drano, did it get hot? Because it says here that the heat produced melts and saponifies the fat that clogs the drain. Were you using your safety glasses when you're using the drain?
Always.
Okay, so before we go on, it says heat's produced. So is this reaction exothermic or endothermic?
Exothermic.
That's exothermic. Okay, so if we consider this an equilibrium reaction, if this has a small equilibrium constant, would we expect to see reactants present or no reactants present after you pour the Drano into your drain and hopefully unclog your drain? Okay, so if there's a small K, would you see a lot of reactants present or few reactants present? Yeah, so if it's a small equilibrium constant, you see a lot of reactants present. If it's a large equilibrium constant, would you see a lot of products or few products? Yeah, a lot of products. So if Drano does work, that means you expect to see aluminum filings and sodium hydroxide pellets still sitting around in your sink or your bathtub or drain. So would you expect K to be large or small? Yeah, so if the Drano works and unclogs your drain, that means that this reaction did occur, so we would expect the equilibrium constant K to be large. Okay, so in terms of Less-Chateaubrier's principle, how can this reaction be shifted toward the product side? So what's one thing that you can do? Yeah, add water. What's another thing you can do? Yeah, add more sodium hydroxide, solid. What's another thing you can do?
That's clogged drain.
Pardon? Now note that this reaction we said is exothermic, so would you raise the temperature?
No.
Or lower the temperature? If you want to lower the temperature, that is you're removing products which would be heat, and as you lower the temperature, that should shift the reaction toward the product side. Okay, if an excess amount of water is added, how will the reaction be affected? Will it shift toward the product side or toward the reactant side? Okay, so you're using an excess amount of water, which means you're adding more water. So is that going to shift the reaction toward the product side or toward the reactant side? Okay, so note that you're adding reactant, which means that the reaction should shift toward the product side. Part D, if hot water was added instead of cold water, would Drano work better? In other words, which direction would the reaction shift if you use hot water instead of cold water? Yeah, so it should shift toward the reactant side, because note that if you use hot water, you're also adding heat. Heat is considered a product, so by adding heat, that should shift the reaction toward the reactant side. So yes, you want to lower the temperature. You actually want to use cold water using the Drano rather than hot water.
What if you just put it in the refrigerator for a little while?
put what in the refrigerator? Well, see, the solid drainer consists of the aluminum and sodium hydroxide. So if you're using a liquid drainer, yeah, maybe you want to stick it in the refrigerator for a while. Because the liquid drainer, I think, already contains water as the salt panels.
What if you use ice? Ice. Pour it down. It's going to make it colder than using water.
Yeah, you can do that. Oh. Okay. Part E, if the drainer was plugged immediately after drainer was added to the clog, would drainer work better? Okay, so you pour Drano down your drain and then you get like a stopper, or you plug the drain, you pull up that knob in the back of your faucet to plug the drain. Is drainer going to work better? Okay, now know what's happening. You have aluminum solid, sodium hydroxide solid, you have water liquid. That produces NaAlOH4 and 3H2 gas. So note that a gas is being produced in here. So if a gas, you have H2 gas being produced. So when you clog the drain, does anything happen to the temperature or the pressure? Yeah, so the pressure is going to increase because gas is being produced. If pressure increases, is that going to shift the reaction in one direction or the other? Now note that in this reaction, how many moles of gas reactants are present? Okay, so we have a solid here, a solid there, a liquid. So that means there's 0 moles of gas reactant present. How many moles of gas products are present? Yeah, so note that we have 3 moles of gas products. We have 0 moles of gas reactants. So we have more moles of gas products and gas reactants. So in this case here, if we increase the pressure, the reaction will shift in a way to relieve or lower the pressure. So if you increase the pressure by plugging the drain, this reaction will shift toward the reactant side, which means that it's going to work better by plugging the drain. No. Come on.
Going back to part D, if the rate constant was proportional to temperature such that you raise the temperature, you raise the rate constant, which would make the rate go faster, but we also concluded that using cold water is better. How do you know which would work?
See, that's the thing. You have to figure out the optimal temperature conditions so that the rate doesn't go so slow that the reaction essentially doesn't occur, versus increasing the yield of product. So by applying the set to H principle, that tells you how you can increase the yield, like the percent yield. But by doing that, for example, if you're to lower the temperature, that's going to decrease the reaction rate. So like I said, most reactions are exothermic, so if you use too high of a temperature, you'll lower your yield where it's not going to be worthwhile in a new reaction. Whereas, the temperature is increasing the temperature, you're going to make the reaction go faster. That's why you want to choose some optimum temperature, and then if you can't find a catalyst to make the reaction go faster too. So, for example, in that reaction we did at the beginning of the semester, in which you made those esters, not only did you raise the temperature, but you also used sulfuric acid as a catalyst. Okay. Because if you raise the temperature too much, that's going to lower your yield of product. And that was the same thing in that aspirin lab in Chem1A, because the same things happen. You use a catalyst, you also use a certain temperature, I think it was 70 or 75 degrees. And, well, I think according to the chemical literature, that's supposed to be the optimum temperature, 75 degrees, as opposed to using 100 degrees, which makes the reaction go faster, but that's going to lower it. Okay, so, like I said, temperature is important, but it'll have 2 effects. It'll increase the reaction rate, but it could lower it. Okay, so let's go on to the next slide here. So we can also determine the reaction conditions for a reaction by applying Let's set the latest principle. So in your car engine, the nitrogen and the oxygen from the air react together to form NO and NO2. So these are the NOx pollutants, which are, I'm not sure if this is listed in your smog report when you get the smog check in your car anymore. Anyway, let's try to figure out the temperature and pressure conditions under which each reaction occurs. So I looked up the delta H formation of NO. It turns out it's 90.4 kilojoules per mole. The delta H formation of N2 and O2 equals, do you remember from Chem 1A? Yeah, so for an element in the standard state, delta H formation equals 0. Okay, so it turns out that reaction 1 is endothermic. And I looked at delta H formation NO2, that's also endothermic. So would you want to use a high temperature or a low temperature for reaction 1? Okay, so since it's endothermic, increasing the temperature should shift the reaction toward the product side. So you want to use a high temperature for reaction 1. Okay, so again, heat is considered a reactant. Adding more heat or increasing the temperature shifts the reaction toward the product side. For reaction 2, same thing. Endothermic, heat is a reactant. Adding more heat or increasing the temperature shifts